So Inspyra is a new module for the StarDrop software. But what does Inspyra do? Well, it really brings the combination of generative chemistry methods and your expert knowledge together to quickly identify and improve optimal compounds. Generative chemistry methods are increasingly popular, methods that will generate new compound structures, new ideas for consideration in the context of a drug discovery project. But they bring with them a number of challenges. First of all, they take a lot of effort and a lot of specialist skill to sort of set up these algorithms and run them in an effective way on a drug discovery project's chemistry. And secondly, they can sort of inundate you with lots and lots of different compound structures, many of which are just not relevant to your optimization objectives or to the chemistries that you want to explore. So really what Inspyra does is addresses some of these big challenges and makes these generative chemistry methods much more powerful in your hands to work in this sort of very seamless way. So what does it do? Well, first of all, it constantly generates, evaluates, and optimizes compounds as you work. It doesn't just propose ideas because the algorithms think they're cool. It's also about dynamically learning from you to make sure that it's proposing the most relevant suggestions for your optimization objectives. So new suggestions are influenced by your interactions and the way that you respond to the ideas that are presented. And in combination, what that enables you to do is very rigorously and objectively explore many different optimization strategies and quickly find those most likely to succeed for your project. Now, the first question that this rightly brings is, well, where do those ideas come from? So the new ideas, the new compound structures are generated based on the compounds that you are exploring, but also on the new ideas that you select and that kicks off the next round of generation. And these are generated using a variety of different methods. The first of those is based on what we describe as medicinal chemistry transformation rules. And what this does is it takes your compounds and applies transformations that represent common optimization steps made in the course of drug discovery and chemistry optimization projects. So it's based on precedents from the literature. We encode a number of very common, relatively small transformations, but also this can be supplemented with the BioStir module that contains over 27,000 precedented transformations from the literature. And of course, this can be supplemented as well with rules based on your own in-house chemistry, your own optimization strategies. The second method is the match series analysis method, which is also in the NOVA module. So these suggestions are based on correlations between the compounds that you've already explored in your chemical series and the data that you have with those in a knowledge base of previously explored chemical series. So it goes beyond sort of simple match pairs to use longer series of matched compounds to suggest more relevant substitutions likely to improve an activity or property. And the final method is based on sort of a baseline of commonly co-occurring substitutions in chemical series. It's sort of like the Amazon model. Chemists who have considered substitutions like yours have also been interested in these. And if you haven't already explored it, they might be relevant for you to consider in the context of your chemical series and your projects. So these are the methods that are used to generate new compound suggestions, and that can generate potentially a very large number of ideas. You can imagine this constantly working in the background. It can explore tens of thousands, hundreds of thousands, even millions of compound ideas really very quickly. So what Inspyra has to do is then say, well, it has to choose those ideas that are most likely to be interesting to you. And so this is done in a probabilistic way. The probability of actually picking up an idea and displaying it to you and showing it to you for your consideration is related to two things. The first is a property of the compound. So you can imagine there might be a preferred range of property values. In this particular illustration here, you can see at the left-hand end of this property scale is where the preferred compounds lie. But it also depends on the chemical diversity. So you might imagine there's sort of a sweet spot here in the middle where it's proposing compounds that are different enough to be interesting, but not too different to be irrelevant. And so you end up with this sort of two-dimensional probability distribution sort of illustrated in a sort of a cartoon form here with this sort of peak at sort of the center left, if you like, of that space. But that's just the starting point from the perspective of probability. It's like a prior distribution, because what it then does is to learn from your requirements. So as you interact with the suggestions and ideas being proposed, this probability distribution can change over time to respond to that and make sure that it's focusing on the most relevant areas of interest. If you're early on in a project, you might be willing to consider more diverse ideas, to spread out and consider lots of different chemical space. And to do that, you might be willing to sacrifice your property value a little bit and consider some things that are perhaps a little bit less than ideal to give you new avenues to explore. Whereas perhaps if you are early on or late on in a project and late in lead optimization, you don't want to make any large jumps. You may be just looking at small refinements around your lead compound. So this approach guides these generative methods to very quickly explore the most relevant chemistry spaces and suggest those optimization strategies that are most likely to succeed in your project. So how does it do this? How does it learn from your interactions? So as I mentioned, this prioritization is based on the combination of a property and diversity to help you to achieve your goals. So what do we mean by a property? Well, a property is a prediction from any model connected to StarDrop. That could be the models we provide with StarDrop, those built with the auto modeler, those from our Sorella platform, or indeed any of your own models that are linked to StarDrop via its modeling API. But it can also be a multi-parameter score made up from a combination of multiple predictive models. So you can define sort of a priori that balance of properties that you're looking to achieve across a range of different activities and properties. And this is using StarDrop's probabilistic scoring approach to multi-parameter optimization. And diversity is a metric of structural similarity to previously selected compounds. In this case, it's a Tanimoto similarity based on a 2D fingerprint. So then Inspyra learns your goals in terms of properties and diversity by responding to 4 very simple actions. And the 4 actions range from selecting a compound. So that's the most positive thing you can do. You say, I like this compound, I want to keep it. I'm going to add it to my data set for later consideration. You can also like a compound. You can say, all right, this compound is heading in the right direction, but it's not quite good enough to keep. So it's sort of a weakly positive signal. You can ignore a compound. You can say, there's nothing wrong with it, it's just not interesting. So this is sort of a weakly negative signal. Or you can reject a compound. You can say, no, I really don't like this compound. There's something wrong with it. And that's obviously the most negative signal. And it will learn to avoid compounds like that. And so it takes the interactions that you have with these compounds and then estimates the likelihood that you will respond positively to a new compound that it's generated, given its property and diversity and these previous interactions. It does this using a sort of a Bayesian inference approach to estimate that likelihood. So let's talk a little bit about that in more detail. Basically, the way that it works to estimate this likelihood is it begins with a prior distribution, sort of like that sort of 2D example I showed you before. Here's a sort of a one-dimensional example in a property space. The prior distribution is saying, to start with it, between 1 and 2 for this property is sort of an optimal range. But then it looks at the distributions of the interactions, your interactions with previous ideas, to transform this into a final likelihood distribution. So what you can see here, it's looking at the distribution of compounds that have been rejected, so with lower values, those that have been liked, sort of moderate values, and those that have been selected, the most positive response, have the highest values. So it says, okay, it looks like prefer compounds, maybe with a higher value than that original prior, in this case in the range of sort of 3 to 4. So it's learning that optimal sort of range from those interactions. Well, that's a sort of a schematic example to show the concept. How does it actually work in practice? Well, this is an example of running the algorithm in practice, just looking at a very simple objective to maximize the log S, the log solubility here. And in this case, we started with a flat prior, so no a priori assumption regarding a preferred range of solubility. And then you can see it starts to learn very, very quickly. After 5 interactions, here you can see that it's rejected some of the low solubility compounds and liked some of the compounds with higher solubility, but none of these compounds have reached a high enough solubility to be selected yet. After 10 interactions, you can still see these rejected compounds are the same as before. Now it started to like some higher solubility compounds that have been generated. And the ones that have been selected are compounds up here between 4 and 6. And now it's saying, okay, now it's sort of keying onto this range here, the higher solubility compounds between 4 and 6. And then after 30 interactions, what you can see here is now actually we've begun to reject compounds with higher solubility, but not the highest, because we found even more soluble compounds. So we're even pushing it further and further. The selected compounds now are up here near the top, and it's beginning to sort of prioritize even more soluble compounds that have been generated. And it's understood that that's what we're trying to do, is to maximize that solubility. But as I mentioned, it can use a very similar approach for chemical diversity. So here's an example of it learning about chemical diversity. What we've set the challenges of selecting from 3 different chemical series. We've just labeled them conveniently A, B, and C here. And in this particular case, the user selected compounds from series A and rejected compounds from B and C. And so what you see is initially it doesn't really know, it's sort of bouncing around a little bit. It's trying some compounds from different series. But very, very quickly, after only 5 or 10 interactions, you can see this distinction emerge. The algorithm has really keyed on to the fact that the compounds most likely to be interesting to the user are from series A, the light blue line here at the top. It's given a lower likelihood for series B, and the lowest of all is series C. It's really moving away from that in quite a strong way. It is interesting to see that there's a bigger distinction between A and C than between A and B. This gap is larger, and we can sort of understand that by looking at the chemical space sort of represented here in a TSNE plot. And what you can see here is series A is this one, it's sort of the very top. Series B is the one here to the left, and series C is the one here in the bottom right. And series C is the largest of the series in terms of number of compounds. But what you can see is that A and B are closer to each other, and C is the furthest away, which is why it's able to learn that stronger distinction. And what we're showing here is that the first 5 compounds picked, essentially with no a priori assumption, they all happen to be in series C, because just statistically speaking, it's the largest, and that just happens to be the 5 that it's picked. But even after the 5th iteration, you can see it's selecting mainly from series A. This is the one that we're selecting, we're liking, and series C here, there's just 1 picked up from that. After 10, now you can see it's basically all series A and B, and it's realized now that series C isn't interesting. And if we just look at all samples over the entire run, you can see the large majority of those are coming from series A, just a very small number from series B, and a few of those sort of vestigial compounds from series C, but it's learned to focus very closely on that most interesting series. Now I've shown an example with just one with a property, solubility, and an example in exploring chemical space, but you can imagine the combination between these two, whereby it learns your preferred series. But if, for example, it finds a compound that is really good in terms of the property in a reasonably similar series, it might say, hey, I know you're not interested in this so much, but you might want to look over here because it's really, really good in terms of the property that you're exploring. So it trades those 2 factors off in a very dynamic way to help you to explore outside the box and look at lots of different optimization strategies, but while focusing on those properties and chemistries that are most interesting to you. So now I'm going to hand over to Peter, who's going to give you a live demonstration of this in action.
Thank you very much, Matt. And hopefully everyone can now see a copy of StarDrop. This should be very familiar to all of you because this is the standard view that you would see within StarDrop. I've loaded a data set here that is directed towards DPP-4 inhibition. It has data for other DPP isoforms and a few predicted properties that deal with decent PK ADME. And we have generated a DPP4 inhibitor selective scoring profile. And so you can see the properties that we have within this scoring profile, that we want to have something with DPP4 activity. We want good phys chem and PK properties here, and we also want selectivity against DPP2, 8, and 9. And we've got a couple of hundred compounds in this data set, and on the visualization on the left-hand side, you can see the range of scores that we've got for this profile in these 4 chemical series that we've defined within the data set. And you can see, really, we're not doing that well. So the sort of design criteria would be, well, we spent time creating a couple of hundred compounds, and we're not really getting to where we want to be. So this is where Nova could come in, because we could take a particular selection of compounds and try the generative methods that we've described, or we can now use Inspyra without having to bias and to set up our conditions for exploring new ways of improving the scoring profile here. I've had Inspyra running whilst Matt's been talking, and you can see in the panel I have got ideas generated, and the property I've told interested in is this DPP4 scoring profile. So what I'm really interested in, trying to increase this scoring profile figure, and really, if I can get above 0.4, I'd be pretty interested. Now, as it happens, all of these structures that you see in the panel, they have red borders, and that means that that structure has a score that I'm interested in that is better than the average here. And so numerically higher than the average will come out as a red border, numerically lower than the average will be a blue border. About the average, it'll be gray. So you can see all of these ideas are actually going in the right way. And so I'm interested in these. These seem to be reasonably good. So I'm going to like these ideas because they're all decent scores. Now you can notice that having liked something, it's then replaced by another compound from that pool of compounds that have been generated. And here we can see one that has a blue border. This is something where the score is now 0.11. So really, I don't like that one. So I'm going to hit the cross that says I dislike that idea. This one is a gray border. It's about average. I'm going to dislike that one as well. It's not great. And that one. And you can see as I'm going through, it's now presenting more in the way of red bordered compounds. Now, this particular compound, 0.64, I really like this compound. I'm going to add it to my data set. So I click on the plus. Now that's a really strong like. And so if I look through here, yeah, here's another one that's above 0.5. I like that. I'm going to ignore some of these because they're really sort of mediocre scores. I've got things that are coming up better. Yeah, I like these. And you can see, oh, this is a blue border. I don't like that one. I don't like that one. I don't like that one because it had the nitroso in there. Ah, 0.53, that's a nice one. And so on. I'm deliberately adding those compounds that have got 0.5 or more. And as it happens, it's also come through with my particular favorite chemical series, which is the cyanopyrrolidines. So again, because I'm adding these compounds to the data sets, this is a strong like. This is a way that it will emphasize that particular chemical series. If I don't like, or I just want to ignore all of these because the scores are mediocre now, I can hit ignore all the suggestions and it will bring back a new set for me. Yeah, here's another one. I can like that because it's 0.5, etc. And so all of these ideas are now contributing to the pool of compounds from which you can make changes. So it's not only a case that you are liking the compound, but you're also adding it to the data set to be then used as another seed which can generate newer, better ideas. Here's one. Yeah, I like that one, even though it's got a cyclopropane in it. I don't like that one. I ignore it. And so on through. And so now that I've been adding compounds to the data set, I can in fact just scroll down and you can find all of those ideas have now been added to my data set. And one of the easiest ways of finding those is that most of the data sets will have an ID field of some description. You can just sort that ID field and then select those rows and put them in a new data set of ideas. And then those are the things that you can now send to other people. You can now evaluate in other ways. And so this is a way that you can use Inspyra without biasing for any particular reference compound. You can just use all of the data and a multi-parameter scoring to generate new ideas. Now that's one way of working. As Matt described, we have not only the panel, which is just sitting there in the background presenting compounds to you, and so saying, hey, do you like this? You can be doing other things and be ignoring that panel and then just come back to it and go, oh yes, I like that, I don't like that. It's happening in the background. So one of the things that some people want to do is to say, right, I've got a particular compound that I'm interested in. So here's one of my cyanopyrrolidines here that I'm interested in. And actually what I'm interested in is it's got a little bit of a problem with hERG. It's 5.3 in terms of the activities here. And so what I would like to do is to think about suggestions to affect that property. So in the design tab, I can select hERG as the property I'm interested in. And you'll notice there are two extra buttons in the design tab now. The first one is the Fragmenter. If I click on that, what the Fragmenter does is it looks at the molecule that is in the design tab and it splits it into rings, substituents, chains, and comes up with suggestions for replacements for a particular area. Now it just selects the phenyl ring at the top here, but I could move the cursor down to this phenyl ring, click on it, and I find I have suggestions. And again, very much like the panel, if I'm looking for a decrease in hERG, I'm looking for a suggestion that has a blue border. So yes, that's got a blue border. I like that particular one. And it's doing more than just presenting me with a couple of suggestions. Here are 3 more. I don't like these because these have now got reddish borders. So I'm going to dislike those. And I'm just using the middle mouse wheel here to scroll my way through the ideas. And I'm just going to see, well, yes, I don't mind pyrimidines, so I can take that one as well. And let's go back to that phenyl at the top. Let's scroll through. Yeah, okay, it's a pyrrole there. So I like it. I don't like that one. Don't like that one. That one. So I'm giving it the steer that I don't like those ones that have higher values. Don't like that one. Just scrolling through, seeing what sort of other ideas come to pass. Now this has got a nice blue border, but there's no way that I'm going to have a quinine, so I'm going to get rid of that. That one's red border as well. Oh, that's an acid. I really like that. May not be wonderful, but we'll see. It really does wonders for the hERG predictions. And you can see that you can go through these areas of the molecule, focusing in on substitutions that should affect the property that you're interested in. And I've now made a couple of selections from different areas. And having made those selections, if I just hit the blue arrow button, then what we think of is that if you like particular substitutions in areas, then the combination of those substitutions may be even better, and it may be something that you'd be interested in creating in a library. And so the use of the blue arrow button here takes all of the substitutions that we made at those various locations and creates that library for us. And so if I just move across, in fact, those particular compounds do show decreased Hg, at least in the predictions. Then something down to 3.6 in some of these. That's probably the acid here. But as we usually say in our demonstrations, optimizing against a single property can lead you into problems when you're looking at a multi-parameter optimization. And you can see for those particular compounds, they are scoring lower than the original compound did. But it gives you the opportunity of looking at a particular key molecule and getting suggestions for properties, even multi-parameter properties that you may not have thought of. The other part about the designer is that, yes, having a fragmenter which takes a molecule and splits it up into these rings and chains may be all very well, but you might want to say, well, actually, I want to take on all of this particular substituent. So if I just get back to that starting molecule that I had, the other button here is something where you can select an area. I'm just using the left mouse button here to lasso around a particular group and saying, this is an area that I want to deal with. Please go away and find suggestions that may affect Hg that compass all of this. And so you have the control of being able to say, this is the region that I want to change. And so again, you get the same sort of principle. Perhaps I will like this one. I don't like that one. Again, red borders here. If I just scroll through a little bit more, see whether there are any other ideas that catch my eye when it comes through. Oh, okay. Perhaps I like this one. Fairly basic change a phenyl ring to a pyridyl ring. Perhaps I'll start with this one. And in this mode, what you can do is just click on a substituent and it will replace it for you. So now you have a new reference molecule where you can then start and look at perhaps another area. So you can say, oh, perhaps I want to now look at this area, and it will go away and find suggestions given the fact that you've liked a particular derivative that it suggested earlier. So in the design tab, you have these different ways of working in terms of being able to focus in on specific targets and yet still use the transformation and the generative tools within Nova and within Inspyra, therefore, to provide ideas on how to improve the properties that you're interested in. In the design panel, this is a lot more general way of looking at holistically at a data set and trying to find suggestions that work well in that set.
Excellent. Well, thank you very much, Peter, for a really great demo and hopefully explore some of the different ways that you can work with Inspyra in StarDrop. I just thought I'd mention for the StarDrop users in the audience that Inspyra, of course, is a major addition to StarDrop. If you'd like to give it a try, please let us know. We are, of course, very happy to give you a chance to try it for free and provide you with some training and help you to explore how it can work with your projects and your chemistry in the future. So again, thank you all very much, and we'll look forward to seeing you at our next webinar, which is coming up soon. Keep an eye out for the announcements. Thank you.